Afternoon, I hope everyone is safe and well. My name is Paul Jones and I'm an application engineer with Zuken UK Limited. Today I'll be discussing how to assign design rules with CR-8000 to help you adhere to any industry requirements. Immediately following the broadcast, I will be opening up a live breakout session where everyone can join in a Q&A. I hope to see everyone there. I'll shortly be going through an overview and then into a live demonstration. Failing to adhere to electrical installation requirements could result in sanctions from governing bodies like UL issuing variation notice. Preventing non-compliance by setting design rules will prevent insufficient spacing between conductors. This should prevent any electrical arc which poses a serious danger to the product and the user. This presentation will concentrate on IPC 2221 Table 6-1. So just to give a little difference between clearance and creepage. Creepage is what you see across the air, and creepage is the distance you see across the surface. So clearance is shown here, slot doesn't matter, whereas the creepage goes across the slot or even through the barrel of a hole, even to the underside, to check the shortest gap between one and another. We're going to demonstrate later how we import master design rules into the schematic diagram. We can do this with a combination of importing rules via the rule editor, setting class to class in the constraint browser, or adding voltage attributes. In this instance, we want to use the rule editor to import master design rules into schematic, as we want to use some of the larger design rule stacks that are available. Opening the rule editor, you can see there are various rules available which can be used in the constraint browser at various stages. But we'll be concentrating on design rule stack, as I can assign the larger rules within the class-to-class clearances. This leads us on to class-to-class configuration. In this example, we're going to show a basic setup for primary and secondary barriers. We're going to show how to treat nets in an undefined class, and also how you can control any NC pins. Finally, at schematic stage, we can select the line and apply nominal voltage. We could also apply min-max voltages in the constraint browser and also assign phase groups if necessary. But the example shown is just going to concentrate on nominal values. Next, we turn our attention to the PCB design. I've chosen a flyback converter circuit as this is a natural barrier in areas of high voltage, which can clearly demonstrate CR-8000 capabilities to adhere to set constraints. I will demonstrate how to set up IPC 2221 settings for uncoded conductors on external surfaces, run design rule checks, and show how to validate your design. I will then follow on to running safety clearance checks, where I can then check for creepage violations. In the demonstration, we are going to pay particular attention to certain nets that we may be concerned that creepage may not be maintained. I will show the effect on creepage when a slot between violating areas has been added and visually show the path that creepage has taken. Finally, we check for clearance violation to mechanical objects. I will demonstrate this by setting up spacing checks between certain conductors and imported mechanical constraint. Show how to validate the results from visual inspection, which you can cross-probe from results window. So this is the first part of the demonstration, schematic capture stage. I'm going to assign net voltages here. I'm going to create class-to-class rules, and I'm going to import master design rules. And then I'm going to show you how you can assign nets into a particular net class efficiently. And then I'm going to close this, forward annotate the changes into my PCB, and then show you how you can check it there. So the first part, I'm going to add some net voltages. If I just select any line, for example like this one, you notice I have an attribute here called voltage. So I'm going to put in here 310 volts. And that's it basically. That's how I can assign that. You'll notice I've done this in other areas. If I just select these lines here on this potential divider, you can see that the net voltage is gradually reducing. Okay, and then in some other cases here you can see I've got some other net voltages applied in these areas as well. Okay, so that's the first thing to do, assign your voltages. The next thing I'm going to do is create my net class, but before that I'll bring in my design rules. So up here I've got a tab that says design rule editor. I'm going to do that, say yes, so that's save at the moment. And we have the design rules already loaded in, but if they weren't, I would load in from my library. I would go in here, select the library that I want, open it, and then select the rules that I want to sort of import into my library. So notice on this one, I have quite a large gap on here, which is a clearance of 4mm. This is what I'm going to use across my barrier, the primary and secondary spacing. So the next thing I'm going to do here is I'm going to go into my constraint browser, and I'm going to create two class-to-class rules. So into here, I'm going to just create primary and secondary. Okay, so obviously we got this matrix now where I can now start to say between different classes, what do I want to set? So the first one is, how do I capture anything I haven't assigned into a net class? And default, you have an undefined clearance class. So here, I don't want to be guessing I've done something right or wrong. So I'm going to put the largest gap. This would mean that if something was in the primary section and it was very close to the secondary section, I catch if it's a large gap is necessary. Whereas if it's in its right area, I'm going to see a very large gap around it, and of course that will make the PCB designer report this back to the circuit engineer to say that's obviously wrong, it needs to change. So I'm going to go into here and I'm going to say that one is set as the larger gap as 4, and the same here, I want to set that to the largest gap as 4. Then I'm going to say primary to primary, so lines which are in there, I'm going to say that gap can be set as 0.2. And then I can say primary to secondary, and I want to set that gap to be 4. And then I can say secondary to secondary, and I can say a gap of 0.2. Remember, there's net voltages which are going to take care of the sort of larger spacings you require within each of these groups. Okay, so that's done. So that's easy enough. The next thing I'm doing is say 4 pins which are unconnected. Obviously they don't have a net on there, so I can't select them to actually assign a class to it. So I set it here and I say what do I want to do. So I say set in classes for NC pins, and then I'm going to say T1, 5 and 6, and I'm going to say I'm going to set that into secondary, and the same on this one into secondary, and do OK and OK to that. Now I can close this. That's all I need to do now here for the constraint browser. So I can close this. It'll ask me if I want to save it. I'll say yes. Then I want to efficiently assign the nets into each of the primary sections, into the primary or the secondary section. So the way I do this, now I've got a nice barrier here. I can just draw a rectangle, but if I didn't, I would go into edit and I'd say select method and a polygon area, and I would say parts in this area here. Oh, let me step back a second. I want to select my select focus to be net object only. Okay, then I want to say edit and select method. I want to say polygon area, and then I can draw a box around the nets that I want to assign into one of my net classes. Okay, so you can just see that my net lines have been selected, and now I want to say what net class do I want to assign them to. So I can go into my assist menu, right hand mouse button, and then I want to say what do I want to do, and I can say net class. This brings up this for me. What I can then say is clearance class or class. In this case, I'm going to set it as a clearance class. I can set it at ENet, or I can set it at net level, and then I can say which class do I want to assign. look through here, I've just got some predefined classes which have come from my rules. So in a case of this, I want to say, actually, for these, I want to assign this as the primary section and apply. Close that, and I'll say yes to that, and I can close my constraint browser. I want to do the same on this side. Defaulted back now to a rectangle, so I can just go through my barrier. Like I said, I have a natural barrier here. It's selected the nets on the other side now. I can invoke my assist menu again, say set class, brings up this again. I'll say clearance class again, scroll to the bottom, and I'll say everything in here is assigned to secondary, and apply and close and say yes to that. So now if I select all my nets here and I go into my design rule, you can see they're all being assigned except for this one. Now I'm not sure why it's not selected that one, so I'll just cross probe this and select that and just take a look where it is. I clearly see that's in my primary side, so I can select that one and I can say primary and do OK. Now I know from looking here, I can see that all my nets are actually allocated into a clearance class. But on a bigger design, this could be pages and pages of net names. I might miss that something hasn't had a net assigned, which is why I said to try and capture those with a large rule at the class-to-class clearance configuration. Okay, so I can just close that. I minimize that. So that's basically it now from a schematic capture side. That's done. So all I need to do is sort of sync the schematic, my PCB together. So I've already forward annotated my changes into my PCB. I've not shown it just to save a little bit of time. So what you'll see, because I don't have the external figures added yet for my voltage check, that even with a large voltage assigned here, I've still got quite a small space. Okay, so I'm going to set that up now. So I'm going to go into my rule editor. And as you can see, I've already got IPC treble 2.1 section B1 set. This is for coated conductors. So I'm going to select B2 in here, just because that's the table value. And then I'm going to start putting in my thresholds from the IPC standard. So the first one is 15 volts, 30 volts, 50 volts, 100, 150, 170, 250, 300, and 500. Okay, just make this a little larger. So those are the thresholds. Then I'm going to say, well, how do I want to apply, what rules do I want to assign to each of those thresholds. So it's 0.1, 0.1, 0.6, 0.6, 0.6. Okay, so that's the sort of static, as you can see, like the graph on the right hand side, where it's sort of stepping up as the voltage changes. Then anything greater than 500 volt, we can then apply a formula instead. So I can select into here, and then I can say, what does the formula tell me from IPC treble 2.1? And it's 0.005. And I could, if I wanted to, add a little bit of a buffer in here as well if I wanted to add a little bit of extra space in. In this case, I can just leave it as a formula value and do OK. Oh, sorry, I didn't press return. Okay, now you can see I've got more of a linear line, which is above here, anything greater than 500 volts basically here. Obviously we'll just go up on this tangent. So that's how you can configure the table to check that to standard. Relatively simple. So all you can see is I've now created this. Okay, the next thing I need to do is then say I want to apply this rule here and assign it to this voltage difference clearance table stack. So I would then say select this one and say for external conductors this one and this one, assign this rule, whereas it's this rule for the internal conductors. When I'm happy with that, I would then say apply, yes, save to that, and OK. And then I just want to make some edits onto my copper plane here just to show you. So if I was to say reshape, just select 2 points, data end. Now you can see those rules have been applied, and you can see as an example where the voltage gets smaller down this potential divider, so the gap is getting smaller as well. I've got a DRC here now, so if I was to run a DRC I would find these errors. So I'll correct those first. I'll just input a line. Okay, as you can see, as I move up here now, automatically, let's just pick that one, that's going to change there, so I'll make a selection here, just move my cursor up. As you can see, I come up to here now, it wants to click back out, so I'll just click one there, and then coming into here you can just see now the different steps, and obviously this gap and this gap will be the same, okay, because this potential and this potential is the same. So that's how you can see that the voltage difference has actually now controlled the space in here. The other thing we did at the schematic side was that we put in all of the nets in my primary section over here into a clearance class called primary, and all the nets on this side in a clearance class called secondary. Okay, so for example, if I was to input this track here across a barrier, notice that I'm trying to move my cursor here, it won't let me go because it's obeying that rule. So I can come in here, for example, and you notice how it will cut through copper, because obviously it's dynamic, but any tracks, it's showing that it's automatically trying to keep that 4mm space. It still doesn't like it there, so for example you can now see that, and again up here you can see it's now obeying a rule up here as well. That's there, and the same this side. Like if I was to come in here, obviously there's a larger space between these rather than the optocoupler here. You can just see it wants to start stopping me from routing up here. I can't push this across here any further, automatically stay into those rules. Okay, so that's that one. So the next one then is we're going to just run a DRC, have a look at where the errors are, and then see if we can fix them or not. If we can't, like in one place on here, I know that I have to add a slot, and we'll do that. So the next part I will run the DRC. I'm going to go up into my check tab, and I'm going to say DRC. I'm going to say check entire area and execute. And as I said, I know I got this one, and I know I can't keep that clearance. So I'd either have to accept it, which obviously I can't do that, it's breaking the rules, or I have to put a slot in. But I also know there's another one here, so look at this one as well. Okay, so in regards to this one, obviously I can adjust those if necessary. It's actually detecting 0.56 there, for example. In regards to this one, I can maybe look at the forming of this part, so I could go into the component, and I could say change footprint, select this part, look for an alternative, the formed one, execute. That's changed the forming on that part. Adjust that track, so I'm happy with that one. Then I could run a DRC, now I've got the spacing I want. Obviously I can correct this one, it could well be just that the copper plane hasn't been cut back. So I could come into here, select this, reshape for example, just select 2 points, data end, that one's now gone, happy with that. This might be this one here, so again, maybe select 2 points. and I guess this one is maybe because of the wires. So again, single click, reshape it, this one, data end, that's that one there. Obviously I would go through the DRC result window to do this really, but for the purpose of this I'm just looking by eye for now. But I know I got an issue here. So what I'm going to do, I'm going to purposely put a slot that's too small. So when I run the DRC, it'll show that the path the creepage is going to take is to the edge of the slot, around the slot itself and onto the conductor, or to the slot and then through the PCB surfaces to the bottom side and then to the conductive pad on the bottom. So I'm going to go into here, I'm going to say slot, that would probably be fine. So I'm going to make this length a lot smaller. I'm going to say something like 2mm, and I'm just going to put it there. Okay, I got an error from here to here. Okay, that was something I probably have to accept. So now the DRC for this one, I would accept them as a clearance DRC, but then I would look at the creepage and say, I've assigned it as the clearance is okay, I'm happy with that. Now the slot is in there, I'm going to look at the creepage. Okay, so in the case of this one then, what I'm going to do again is on the check tab, and I'm going to go into my safety standard check. And it's this one of particular interest to me. Select the net, okay, and then I'm going to say a search distance around here. I know the rule is something like, because this is 310 volt, from here to here is about 2.5mm, but I'm going to just expand that slightly to say the search distance around this, I'm going to look for 5mm, and I'm going to execute. Okay, now if I bring this up here, you've got my layer lists here, so it says from layer 1 to 1 or layer 4 to 1, for example. How is it now passing that condition that I've got? Okay, remember this is a 5mm spacing, so it's also potentially looking to other nets as well. It could be, looking up here, for example, to this net as well. Okay, so I would go through here. Obviously I got some cautions. Okay, it's within the value, so I'm happy with that. Or I could go back to my rule and dynamically make it a little larger. Like I said, you could change that if you wanted. But I would concentrate on these fails. So you can see on this one, that's obviously on layer 1 to layer 1, it's got a fail. It's only measuring. Let me just put the cross probe on. If I select this one, it'll cross probe to it, and it shows, as you can see, it's just bending around the slot slightly. If the slot was bigger, then it would be fine. So in the case of that one, it's not very good. But then this one is the interesting one. We're now saying, even though we got a slot in, from layer 1 to layer 4, it's still measuring a fail. Okay, and the best way to look at this is to go into 3D mode. So I'll just move this off my screen a second so you can see in 3D. Go into 3D, if I just zoom out a little bit, just pan around on these. Let's just make, let's turn off my components for a second. Let's just move this a little bit up. So I think that's clear now for everyone to see. You can see that off the top surface, it's going across the top surface. You can see it going down the barrel of the slot and then to the bottom surface into the conductive pad that's on there. Obviously the conductive pad not visible, so you can't see that, but if I put that on, you can just see that conductive pad just come up there. Look. Okay, so that shows then that you could run the safety clearance check. This would pick up these, and again you would say, right, okay, so I'm not happy with that. I would then change this slot maybe for a different slot. So I'll select this slot, bring up my property menu, change the length from 2 to 5, apply that to that, that's okay. Let's close that. Let's run a DRC, check more errors again. Once he's found the errors, let's go into my error list. I've obviously got these ones here. I'll just bring this down here. We have this one, which we're aware of. We now know that we have slot in there. That should be okay. That's the same error. And then I've got the error messages from the slot to the pads myself. I'd have to look at this measured value is within the fabrication capabilities. Go through each of these. Again, that's the same one. Got a slot there to help with that, and again, and then I've just got a component to the board edge. That's the problem. So I would close these and say approved, add some comment. To each of those. If I wanted, obviously cut and paste if need be, and then close that. So then let's move on to run the safety standard check again. Going to select the same net, and this time I'm going to execute. And again, if I look through my list now, I've got the same cautions I had before, what I measured, but now I've got no errors. The slot that I've added is doing its job. So I just close that. Finally, we're going to do a check from the PCB to the mechanical assembly. So I'm going to specify system config file. I have one prepared here. If I go into flat view, and if I just zoom out a little bit, you can see my mechanical assembly. I can expand some of these. It looks as if some things are not visible, so just go for put the cover on as well, and then I can minimize that. So what I can now do is a clearance check, 3D clearance check. So I can go into my check settings and I can say let's create some rules. So I can add an item. So let's just, as an example, say conductive. Return on that one, and I could then say add another one here and say component. So I can have multiple checks running at one time. So I concentrate on the conductive one. So I'm going to go here and I call a rule. I'm going to say 310 volt underscore to chassis. Okay, that's just a name, it can be called anything. I'm then going to say what type of things do I want to check. So I'm going to say I want to check a net, and then I can browse into my net names and say 310 volt is what I want to check. And I say what do I want to check it to. If I drop into here, you can see I can check it to components, comp conditions, nets, or mechanical condition. Okay, mechanical data, sorry. In this case, I'm going to say mechanical data. I'm going to click into here, and I'm going to select this step file that I have. And I'm going to specify, I don't know, something like 20 mil. Just make sure I can bring an error up to show you. And then I'm going to say, yes, I want to make this check. Okay. I can then save this if need be as a parameter file for reuse later. In this case, I'm just going to leave this one in there. Close that, and then I can do this, a 3D clearance check. Yes, I want to run it. It's gone away and it's actually found an error for me. So it said, let's expand this. So this rule that I set at 20 millimeters has gone away, and it said it's actually found a clearance violation of 10.85. So I can double click on that. You can just see this coming up here. It just stays on there for me. So you can see it's 10.85 from this pad here, and then to the sort of mechanical sort of base that we can see there. It's quite difficult to see, but I just go down here. You can just see from here to the base of the sort of mechanical housing. Obviously, you would either have to make some changes to that, or you'd accept it, or change the rule, depending on what you want to do. So that's the end of the demonstration. So in summary, what we've done is we've added some rules at the schematic stage. We brought those rules forward into the PCB. Within the PCB then, within our rule section, we've set up some voltage clearance classes, and this time we've based them on IPC treble 2.1.
and I showed you how to enter the external conductors uncoated. Then we run a normal DRC, fix the errors, and then we've run a safety check, and we've noticed that we need to add a slot. We deliberately made the slot too small so you can actually see the path of the creepage. Then we've changed it, added a larger slot, run the safety clearance again, showed there's no violations. Then we've gone in, created a rule to check the PCB against a mechanical housing, run that check, and again we've validated the check. So that's the end of the presentation. Hopefully you've taken something out of this, and please join the breakout session later on. Thank you.